All right, so our last couple screencasts here have been kind of complicated, and I recognize that, and it's very normal to be a little fuzzy on all this. So let's just try and recap how an action potential works. Basically, you've got a high concentration of sodium outside the cell and a high concentration of potassium inside the cell. So when the cell is depolarized or given a little signal, that causes the sodium to rush into the cell and the potassium to rush out of the cell because it causes the ion channels for these two ions to open up. Okay, so it's a bit like doing the wave. Sodium rushes in, potassium rushes out. That action potential in this part then causes depolarization in this next part of the neuron, which triggers an action potential here. Those ion channels open and sodium rushes in, potassium rushes out. That action potential triggers depolarization over here, which causes these ion channels to open. Sodium rushes in, potassium rushes out, and so on down the entire length of the axon. So basically you can think of this like doing the wave all the way down the length of the cell. And that is how electric signals zip up and down your arms and legs and to your brain and back. So it's pretty complicated, but it's your brain, which is complicated. So one final little piece to this is I want to talk about that myelin sheath. We said that it speeds up the signal, but how? The way it works is it kind of allows the signal to kind of hop from one node of HOME-VA to the next. So to illustrate this, what I'll usually do is I'll have a whole bunch of students line up. Just imagine, let's just say I have 100 kids all lined up in a row, and they represent the length of this neuron. And I say, okay, I'm going to be over here, and I'm going to put a stool over there, and my goal is to get this last kid to kick the stool over. But I need to signal that kid. How is it that I, way over here, can signal a kid way over there to kick the stool? Well, it's simple. I do this. Sodium rushes in, potassium rushes out. And the kid standing next to me is like, oh, he did the wave. I'm supposed to do the wave. Sodium rushes in, potassium rushes out. And the next kid, sodium rushes in, potassium rushes out. And basically the wave comes down, and then it gets all the way to that last kid, and then that last kid kicks the stool. So without saying a word, I'm able to signal that kid to kick a stool far, far away. Now, the myelin sheath introduces these little gaps, these little nodes of HOME-VA, and then there's this sort of wrapping around there. So instead of 100 kids, now we only have a kid at each of the little nodes of HOME-VA. And so you can imagine instead of, it's actually the wrong direction, but I'll go from this way anyway. But you can imagine if I do the wave here, now instead of 100 kids having to do the wave, here's a kid doing the wave, and then it jumps to this kid who's kind of far away who does the wave, and then it jumps to this kid who's far doing the wave, and then jumps to this kid. So basically the myelin sheath allows it to kind of hop. The signal kind of jumps from person to person to person. So if we raced, 100 kids trying to do the wave to the very end versus, 20 kids trying to do the wave to the very end, the 20 kids are going to be able to do it faster, and that's how the myelin sheath lets your body send signals faster. You may have heard of multiple sclerosis, or MS. This is an autoimmune disorder where your immune system actually destroys the myelin sheath. So here's a nice healthy myelin sheath wrapped around that neuron. And here it is in multiple sclerosis. And we don't really know why the immune system is attacking the myelin sheath, but it is. And so as a result, your nervous system can't fire as effectively as it should, and it can lead to all sorts of problems, most of which involve the nervous system in some way. Numbness, tingling, vision problems are very common. And that sort of thing. And the bummer about multiple sclerosis is it does regress over time, which means it kind of gets worse and worse over time, which is unfortunate. Okay, so now hopefully you understand how a signal is able to travel down the length of a cell through this series of action potentials. But now we have a new problem. Somehow we need to get that signal to transfer to the next cell, right? There's many cells in a chain that run up your arm, to your brain. So what happens at the end of the cell? Well, at the end of the cell, there's this little space called a synapse. And a synapse is the gap between the synaptic terminal of one neuron and the dendrite of another. In other words, there's a little gap between two neurons. So we need a different system to get that information across, and action potential isn't going to cut it. So let's again do player's process. The first player are neurotransmitters. These are chemicals, and their job is to simply travel across that synapse and relay a message from one cell to the next. You have likely heard of some neurotransmitters. Adrenaline is one, dopamine, serotonin, endorphins, acetylcholine. These are chemicals that, I don't know, people have heard of, and here's their molecular structure. And there's many different types. The next player are the synaptic vesicles. Vesicles are just these little circular structures. They store the neurotransmitter. That's their job. Um, and then finally, receptors. You can see the receptor on this side of the cell, and these are proteins that bind to the neurotransmitters and then initiate an action potential in the next cell. And so here's a picture of one. Here's a little receptor. When the neurotransmitter binds, then that opens up the gate of this ion channel, letting ions pass through. So to understand the process here, put this together, this diagram is available on that study guide that I encourage you to print off. You could take notes on that if you did so. Otherwise, you could just write it in a list, knowing that you have this available digitally as well. So the first thing that happens is an action potential travels down the length of the axon and reaches the end of the cell, the synaptic terminal. Then and there's that action potential. Then if you look at the diagram, you can see that that causes the synaptic vesicles, which are storing the neurotransmitter, to release the neurotransmitter, and the neurotransmitter is going to travel across the synapse. Once those neurotransmitters travel across the synapse, you can see them attaching to these receptors. So the neurotransmitters bind to the receptors on the next cell, and then that signal is going to be initiated, a signal is going to be initiated in the next cell. Now, if you're writing on this diagram, write really small because I'm going to cram a whole bunch of stuff into this box. It turns out that the signal that's initiated in the next cell can be either excitatory or inhibitory. What does that mean? Well, an excitatory signal is one that depolarizes the next cell. That is, it makes the charge slightly more positive, and that increases the chance of an action potential. Okay? Now, think back to what you understand of action potentials. If it's depolarizing the cell, do you think that would open sodium or potassium channels? So think of which direction sodium and potassium go. Does it go inside, outside? And it's kind of a tricky question, but if you can answer it, you're understanding this. The answer is excitatory signals open sodium channels because they would allow sodium to rush into the cell, which brings the charge more positive. Now, the signal could also be inhibitory. An inhibitory signal hyperpolarizes the next cell. It makes it more negative. That decreases the chance of an action potential. And again, think through which one would that be? And by process of elimination, it's potassium. And that's because potassium ions exit the cell. So we're losing positives. It makes us more negative. So here's kind of a diagram that kind of shows we're at rest, minus 70 millivolts. An excitatory signal is going to bring us more positive. An inhibitory signal is going to bring us down. Now what happens is every neuron is connected to tens, hundreds, even thousands, even tens of thousands of other cells. And at any given moment, it is getting messages from all of that huge number of cells. Some of them, indicated in green, are excitatory signals. Some, indicated in red, are inhibitory. So how does a cell know what to do? Well, it's a little bit like a game show contestant. If you've ever seen the show Deal or No Deal, basically the contestant has to decide, do I take the deal that's been offered or do I hold out for something more? And as they're sitting there deciding, the audience is screaming at them. All these excitatory audience members are saying, deal, deal, deal. And all these inhibitory audience members are saying, no deal, no deal, no deal. And that's how your neurons are too. They're getting all these signals. Deal, deal, no deal, deal, no deal, deal. If the sum of all of those messages reach a certain threshold, this causes the ion channels, those sodium ion channels and potassium ion channels, to open. And once they open, sodium rushes in, potassium rushes out, and we have an action potential. That's what summation means. We sum all of these signals together, and if there's enough positive charge introduced, then the action potential is fired, we do the wave, and then it's going to travel to the neuron. If there's too much inhibitory, then it won't, and then it doesn't fire. Okay? So the final process here, once that signal, excitatory, inhibitory, whatever it is, has been passed on, the last step is that we have to remove the neurotransmitter from the synapse. And there's two ways we can do it. The first way is with a reuptake channel. In a reuptake channel, what happens is they just are proteins that move the neurotransmitters back to the original cell. So here you can see the synaptic vesicles. They're releasing the neurotransmitter. The neurotransmitter binds to the receptor, sends its signal, and then the neurotransmitter comes back through the reuptake channel and is recycled. Okay, so that's one way to get rid of that neurotransmitter. The other way to get rid of the neurotransmitter is to have an enzyme simply break it down. So here's a neurotransmitter, acetylcholine. It's released into the synapse. It binds to the next cell, and a little enzyme, it's called acetylcholinesterase, chops it up and destroys it. And if it's destroyed, then that's that. The key, though, is that we have to get rid of that neurotransmitter, because if we don't, it is going to keep stimulating that next cell over and over and over, which creates problems. Foreshadowing for our next screencast. So to kind of recap this, I'm looking for a diagram to recap it here. I'm not finding what I want. Here it is. We now understand this big picture of how nerve signals are sent throughout our body. As the nerve signals are sort of zipped along the arm and to my head and then back down to my leg and all these things, we can visualize that as this series of action potentials doing the wave along the length of the cell. When it gets to the end of the cell, a neurotransmitter shoots across to the next cell, and then action potentials continue and do the wave. So as the signal travels like up my neck, action potential, action potential, action potential, and then it gets to the end of the cell, neurotransmitter, action potential, action potential, action potential, neurotransmitter, all along this chain of neurons. So hopefully by now you are piecing this together. This one is probably one of the more complex concepts of the entire course. So take some time to kind of go over that, reflect on it, think it through, and hopefully you'll get there. I'm available to help. Thanks.